Hi again, welcome to the second video in the differentiation series. In this video we extend our technique of differentiating by first principles to develop a quick way to find the derivative so that we do not have to go through all the steps outlined in video 1. They're time consuming. We need to be quick because we will be differentiating so often, for many of us, daily. In subsequent videos we extend the approach further to more involved formats. To begin, we take the example from the first video whose derivative function we know already to demonstrate the technique. The equation we used in the first video was y equals x squared minus 2x plus 4. So to calculate the derivative function without first principles, we're going to follow all of these steps. dy dx equals, write that down. The first term is x squared, write it down. Now we bring the index down to the front, so the 2 comes down to the front. We rewrite the x, and then we, step 3, take 1 off the original index. So 2 minus 1 is 1, so we're left with 2x. And we repeat these steps for each of the other terms. So the next term is minus 2x. That's really x to the 1. When we bring the 1 down to the front, it's 2 times 1, so it's still 2. X to the 1 minus 1, which is 0, so x to the 0 is 1, so it becomes minus 2. The 4 that is at the end is a constant in the original function, so it's what we call a location constant. It simply moves the curve up or down, but it has no effect at all on the gradient. So we will never, in differentiation, consider the constant term. We only focus on what affects the gradient. Now we can look at a second example. We'll take y equals 3x cubed plus 6x squared minus 5x plus 10. Take the first term, 3x cubed, leave the 3 out the front. It's just a decoration. The x you can rewrite. Then the 3 for the index comes slowly down the front to become a 3 times 3x, and then we take 1 off the index, which is 3 minus 1, which is 2. For the second term, we have 6x squared, so rewrite the 6, decoration. X, rewrite that. 2 comes down to the front to become 6 times 2. X to the 2 minus 1, which is 1. For the next term we have minus 5x, rewrite the minus 5, decoration, x to the 1, 1 minus 1 gives us 0, so we're left with a 5 there. So tidying up, we have 3 times 3, which is 9x squared, plus 6 times 2, x, which is 12x, minus 5. Now if we wanted to use that equation for the derivative, we could ask what is the gradient of the curve at when x equals minus 2. So we just substitute into our dy dx equation, and we have 9 times minus 2 squared plus 12 times minus 2 minus 5. Tidy it up, maybe in your calculator, you get 7. So the gradient of the curve at x of the original function, y equals, at x equals minus 2 is 7. So the curve is increasing at that time fairly quickly. Just a quick note on nomenclature. We noted earlier that we can write the original function as y equals something, and that led us to writing the derivative as dy dx. Or we could have used fx, and that would have led to us writing the derivative as f dash x. Now there's no real difference between these two ways of writing it. Both statements came from Leibniz, the famous German mathematician. Newton, in contrast, used the symbol y dot, which is also acceptable but more limited. If you want more information on these two guys, go and have a look at the calculus main page. Riveting stuff. I suggest you keep to the format in the question you are answering. So if you are asked to differentiate an expression of the form y equals, then write the derivative, in other words the gradient function, as dy dx. But if the question asks you something about fx, then write the derivative as f dash x. We will use Newton's method or format, especially for questions involving time and speed, but these will happen later on in the course. A second format that we could be faced with in doing an exercise is the use of simple brackets in the equation. For example, we might just have 2x squared bracket x cubed plus x bracket. So the x has an index, but the brackets don't have an index, and that's the important thing, no exponent. When they do, then that format uses a chain rule, which we'll talk about in a subsequent video, but here we just expand the brackets by multiplying them through, and then we differentiate. We can't differentiate as it is. So expanding, we have 2x squared times x cubed, which is 2x to the fifth, plus 2x squared plus x, which is 2x cubed. Now we do our normal thing. dy dx equals, rewrite the 2 because it's a decoration, bring down the 5 index down to the front, so it's 2 times 5, rewrite the x, take 1 off the index, 5 minus 1, plus, second term, 2, rewrite the 2, bring the index down the front, rewrite the brackets, take 1 off, 3 minus 1, tidy up, 2 times 5 is 10x to the fourth, plus 2 times 3, 6x squared. Nice and straightforward every time. Get the rhythm. We talked earlier a little bit about nomenclature, and here's another variation. That's the use of the prefix d dx outside of the function that we have to differentiate. Now, there's nothing special about this. It's just another way of asking you to differentiate a function or an expression with respect to the independent variable indicated. Here it's x. So, as someone once said, just do it. For example, if we have d dx of 4x cubed minus 5x squared plus 142, rewrite the 4, bring the 3 down the index, rewrite the x, take 1 off the index, 3 minus 1, go into the second term, minus 5, just write it down, decoration, bring the 2 down the front, rewrite the x, take 1 off, 142 is just a location constant, ignore it, tidy up, 4 times 3 is 12, x, 3 minus 1 is 2, 12x squared, minus 10x. Sometimes we'll get an equation or an expression given to us that we have to differentiate that uses radicals, that is square root signs or fifth root signs and so on and so forth. When manipulating indices, it's common to change between the use of radicals and the use of indices. So if we're given a radical, we can convert it to an index. For example, if we have 2 root x, we will rewrite that as 2x to the half. And the fifth root of x squared minus 3x plus 5 can be written as x squared minus 3x plus 5 to the fifth. Continuing with the first of those examples, we could find the derivative of 2 root x, which we've now written as 2x to the half. So the derivative is, rewrite the 2 because it's a decoration out the front, bring the half down the front to times it, rewrite the x, take 1 off the index, which is a half minus 1, and the 2's cancel, leaving us with x to the minus a half, which we can write as 1 over x to the plus a half, and using the radical, that becomes 1 over root x. Rewriting a radical in this way is all we need to do when differentiating, although sometimes we might want to combine exponents to make the process a bit easier. But the strategy of differentiating is exactly the same in all cases. For example, if we have the expression x root x, fairly common too, this can be written as x times x to the half. Add the indices, we get x to the 3 over 2, and that differentiates to 3 over 2 x to the half, which we could write as 3 over 2 times root x. The fifth type of format we can be confronted with is the use of negative indices. Now, there are no special considerations when negative indices are encountered in differentiation, except be careful. The main caution is to leave the coefficients where they belong. Don't fiddle with them. So if we have y equals 2 over 3x to the fourth, we're going to leave the 2 and the 3 where they are. It's only the x we're differentiating, so it's only the x that's going to move. We can't differentiate an x term or an independent variable in the denominator like that. So we have to bring it up. So it becomes 2/3 x to the minus 4. Proceed as usual. 2/3, rewrite it down, it's a coefficient, times, bring the index down the front, minus 4, rewrite the x, take 1 off the minus 4, it becomes minus 5. So tidy it up, the result is minus 8 over 3 x to the fifth. Easy. The last format we will deal with in this particular video is where we have one term in the denominator. Keep your eyes open for this one. It's often used to trick you. Sometimes we're presented with a function or an expression which is a structure such as y equals 2x cubed minus 5x squared plus 3 all over x squared. The thing to notice here is that there is one x term in the denominator, nothing else, no constants, no nothing. It's just an x, and in here it's squared. So that's what we're looking for, one term in the denominator. We could use a thing that we'll come across later on, that's the quotient rule, but that's going to be a lot harder. This is easier, and we're going to divide each term in the numerator by the term in the denominator. The chances of making an error if we use this approach are going to be substantially reduced. So we do our division, and we have 2x cubed over x squared, which is 2x, minus 5x squared over x squared, minus 5, plus 3 over x squared, 3x to the minus 2. So we take our derivative in the normal way. dy dx is equal to 2 x to the 1 minus 1, which is 0, therefore x to the 0 is 1, so we're left with a 2. Minus 5 is the location constant, so that drops out. And then we have plus 3 times minus 2 minus 6 x to the minus 3, which we can write with positive indices, 2 minus 6 over x cubed. In summary, differentiation is an easy process, but you have to follow the same rhythm each time you differentiate so that when you're under stress, you don't try to do something different. You just follow the same steps. These basic structures depend on having the pronumeral in the numerator. And the sequence that we're going to follow is, for each term, bring the index of the pronumeral down to the front, rewrite the pronumeral, subtract 1 from the index. The formats we have reviewed in this video are first, basic structure with single terms and positive indices. That's the fundamental type. Second, expressions with simple brackets with no indices for the brackets. Thirdly, the use of the nomenclature dy dx. Fourth, the use of the radicals, that's the square root signs, cube roots, and so on and so forth. Fifthly, the use of negative signs when terms are changed from a denominator to a numerator. And finally, there was a fraction with multiple terms in the pronumeral in the numerator and a single term with in the pronumeral in the denominator. So you now have the steps to apply to be able to do a wide range of differentiation. Just keep watching out for the variations in the format of the questions you're asked. Hope I have helped you to clarify the approach. Thanks for watching this video. In the next 3 videos in the series, we look at ways to differentiate more complex formats, called the chain, product and quotient rules. Hit the like button and subscribe if you haven't already. Helps you keep up to date with as more videos are released. Also, go and do some questions in Test Yourself 1 on my website at drjaysmaths.com. Add a comment below or send me an email if you have any questions. Good luck. Catch you later.